Okay, so today, Kenny Rogers' inspired lecture is about gambling. In particular, we're going to talk about randomized algorithms. So we're going to know when to hold them, know when to fold them, and analyze various problems that use randomness for their solution. So the broad overview this week is today we'll talk about randomization, four very cool problems. And next class on Wednesday, we'll talk about cryptographic algorithms. So encryption, hashing, commitments, signatures, those type of algorithms, all of which require randomization in order to achieve their security properties. So, and tomorrow, Wednesday, there should be a review for the exam. The exam will be, again, a take-home that I'll hand out on Thursday. And I'll also hand out extra credit problems for those of you who are wondering how to recover from bad previous assignments. There'll be some extra credit for you to solve over the reading period. So the first problem that I want to suggest was inspired by this film that my 4-year-old wanted to watch over Thanksgiving break. So here is this setup for this particular problem. So here you are. You are the prince of a very wealthy regime, and you have a very bad uncle, which is the setting for any Disney movie in the last 10 years. And you're a prince, but you're an adventurous prince. You're not about to be king yet, and so you're going to go camping. You're going to go on a camping trip in the mountains because you live in a mountainous region. And of course, you're going to go to the camping store to buy all of your camping goods. And part of your camping goods is anybody who's gone camping, you must have a set of matches, right, to create a fire. Unfortunately, your evil uncle owns all of the camping stores in your regime. He had a monopoly, he got a special contract, he handles all of that business for your country. So here's the thing, he's going to sell you a box of matches, but you know that if you perish in this camping accident, then your uncle becomes king and he takes over the entire regime. So the question is, when you buy this box of matches, how can you make sure that you'll eventually be able to start a fire? Buy a box of matches that has 100 matches in it, and obviously you can take one match out and strike it and see if it works. But of course, once that match works, you have no idea, you can't use that match again. Everybody understand the problem? You're given a box of matches, you want to make sure that you're able to start a fire. Let's simplify the situation, assume that as long as you have one good match, you'll succeed in starting a fire. So what can you do?
Buy 2 boxes.
Buy 2 boxes, okay. But your uncle owns the entire box matchmaking empire. So you can buy 2 boxes of matches and he can give you 2 boxes of crappy matches. He's selling you the matches. You're the prince, he's the uncle. You die, he wins. That's the guarantee. And you die, you're going to freeze if you can't start the fire. Yeah. You don't. That's what you want to test. You want to make sure you're about to go camping, you buy a bunch of matches, you got to make sure you can start a fire. Clearly, you can take the box, say, okay, let's see, is this good a match? Take one, strike it, and see if it works, and say, obviously my uncle's a good man, and these matches are great, I'm going to go camping. Right? But he could have, what could he have done?
Put 1 in there that works.
Exactly. So 100 matches, he made 99 bad, he put 1 in there that works. And he's like, okay, well let's be Kenny Rogers here and know when to hold them. So I give him the box of matches, I get lucky, I win the lottery with 1% chance, he picks that one match which works, he goes camping, aha, I become king. So all of a sudden, I have a 1% chance of becoming king.
I have a friend buy the matches, he doesn't know.
Oh, he has intelligence network here. His NSA level surveillance. He knows all about your texts and your emails. And he knows your friends. He follows you on Facebook. Question. What? What do you mean identical? Aha. But this guy is a smart guy. So he knows that that's exactly what you're going to do. So what he's going to do is give you, hey, yeah, okay, here's your first box of matches. Go ahead, test them all. They all work. Okay, here's your second box of matches. Okay, so then that's the question. What is the best you can do? How do you maximize your chance of becoming king? Okay, so I'm going to explain. If you do 99, right, what happens if he puts one bad one and 99 good ones, and you did that? He still has a 1% chance of becoming a king, right? Okay, so spend 2 minutes with your neighbors trying to figure out what the best way to do this would be. You want to survive and become king? What's the best strategy? Okay, so I've heard a good idea from some of you. A lot of you are thinking out of the box. Yes, go buy your batches from Switzerland, go hire a private consulting firm, or just take the box and trust your uncle. So there are a lot of. What I'm trying to get at is randomization is going to give you a very good strategy at surviving this task, even if you only buy one box of matches. Okay, and so here is one idea. Of your 100 boxes, randomly pick 50. Test them all out. If one fails, if one single match fails, then you know your uncle is basically trying to screw you, so cancel your camping trip. If they all succeed, accept it. This strategy has a very high chance of making you king. Let's try to analyze how this actually works, okay? Okay, so let's consider the 3 cases. Okay, your uncle has taken this box of matches and he has polluted. He's messed up a certain number of those matches. Okay, suppose he tampers with less than 50 matches. So he leaves at least 51 matches intact. What's the outcome of your camping trip? Okay? Because either what happens is you find one bad match and you don't go camping. So you find one and you don't go camping, or you tested 50 of them and they all worked. He tampers with less than 50, so he tampers with at most 49, and so you have one good match. You live. Okay? Similarly, if he tampers with more than 50 matches, what happens? You kill the uncle. Because you catch him. For sure, right? If he's tampered with more than 50 matches, you're going to pick a set of 50, means you're going to find at least one bad one. Okay? So what if he tampers with exactly 50? Here is your only vulnerability. This is your Achilles heel. Okay? So in most situations, you're going to pick one of the bad matches and stop your trip. But this is the only chance that you die here is that he messed up 50 of them, and you picked exactly those 50 that he messed up. Sorry, exactly the 50 that he didn't mess up. So all the good ones you tested, now you're left with a box of half full of bad ones. Okay? So, one chance of failure. Okay. So now the question is, there are 100 matches, 50 good ones, and you pick all 50 good ones. What is the probability that this event happens? 100 matches, 50 good ones, you pick those 50 good ones. This is a good way, yeah. The first one, you picked a good one. The second one, you picked a good one. Of the remaining 49, there are 49 good ones, 99. Okay. Another way to look at this is the number of ways that you can pick 50 matches, 100 choose 50. And there's only one way for you to pick the combination that does you in. Okay? And this value right here, a good identity to remember. So So in other words, it's roughly 2 to the negative 98, something like that. This is called Stirling's identity, or it's by Stirling's identity. It's a combinatorial fact that you might want to. In this case, the best strategy is to pick half and test half and use half. Yeah, that's not always the case. In these particular parameters, it is the best thing to do, and that's why you analyze it like this. If you put it in a calculator, roughly your probability of death is 10 to the negative 31, which is, I guess, close to that other number. It's very small failure in this case. I want to quantify the magnitude of this probability in a few ways. So if you go to Las Vegas and you try to play poker, your chance of getting royal flush are, let's say 10 to the negative 5, right? So this is like, you got a royal flush, and you got another royal flush, and another one, so you got 6 of them in a row. And here's another example. This is a very alarming demographic here. In 1990, if you're age 20, okay, this is the probability that you don't make it to age 21. Okay, so this is like 10 to the negative 3, right? Depending on if you're in the US, with 0.1% probability, you're not going to make it to 21. Of course, it's not a uniform choice here. It depends on what your economic and social status is and where you live and so forth. But it's certainly remarkable that this number is pretty big compared to that number, right? Okay. Very good. So this idea of picking half, it's called cut and choose. And it's actually used in several cryptographic protocols. So for example, with my grad student a few years ago in his PhD, it involves analyzing this type of cut and choose strategy for protocols for secure multi-party computation. In that case, it was actually better to do 2/5, 3/5 checking. There was a slightly different condition that you needed. You wanted to make sure that the majority was correct, not just one was correct. And so there was a different trade-off. But the point is, that simple technique of picking some half, checking them, and using the other half, that's a very, very powerful technique. In all sorts of cryptographic protocols, if you want to check that some other party is doing some operation correctly, not cheating you, then you run a protocol to some point, and then you have them open or reveal that they've actually followed the instructions correctly on half of these, or roughly 60% of these. And if you do that properly, you can sort of ensure honest behavior with that sort of cut and choose problem. So it's a very important technique, and it's based on the simple probabilistic analysis. First example of randomness. Question? No, because if let's say he has messed up 51 matches. There are only 49 good ones. So if you pick 50, you could possibly pick the 49 good ones, but you'll be guaranteed to pick at least one bad one. If he messes up more than the majority, that means that there are less than majority good ones. There are less than 50 good ones. And so if you pick 50, you're guaranteed to pick one bad one. Yeah. Okay, so that's the first example of use of randomness. The second one I'm going to talk about is a more algorithmic sort of task. So imagine you have a very big database. Okay, Alice has a big database and Bob has a very big database. Just call it your disk. So Dropbox, an example of you have, let's say both of these people are cooperating. So you have some hard disk on your computer, and maybe you have 2 computers, and you want to sync them, and you want to see if they're actually the same hard disk or not. And let's imagine that these are, several gigabytes. So let's say it's like 10 to the 8 bytes. Okay? You don't want to send 10 to the 8 bytes in order to check whether your disk is equal or not. Right? So this is a second example of randomness. Here is a protocol that we consider. You pick some prime number, p. And we'll talk about how big this prime has to be. And then what you do is you compute A mod P. So take your disk drive and look at every byte of that disk and lay it out in some order and pretend that's a really, really big number. And take this number mod P. So you can do that by dividing, essentially, take your very big disk and divide it by P and consider the remainder. And division, you can use simple division. So you can just, read the first byte and, just like you did in grade school, subtract and, carry and subtract and so forth. So computing mod is essentially linearly scanning your disk. You have to look at your data in order to tell whether it's the same as Bob's or not. So that's kind of unavoidable. But here all you're doing is taking your very big disk of size 10 to the 8 and computing it mod some prime P, which you'll later see is... So you're going to compute this A mod P, and you're going to send this value, A mod P, to Bob. We'll later see that this P can basically be something like 64 bits. Or if you want to be a little bit more careful, 128 bits. Very, very small amount of information. And now what Bob is going to do is he's going to compute B mod P and check whether, let's call this X. So I'm going to compute it locally, A mod P. I'm taking my disk, computing it mod P, sending it to you. And you're going to take your disk, compute B mod P, and check whether the value I sent is equal. Does everybody understand the protocol? Very simple. So, if the disk A is equal to the disk B, then this protocol certainly succeeds, right? If our disks are indeed equal, then certainly computing A mod P and B mod P is going to produce the right value. So the only question becomes, what happens when they're not equal? So in most cases, it seems reasonable that if they're not equal, then the protocol will actually correctly tell you that they're not equal, right? But then there's some small chance that this protocol convinces that their data is equal. So for example, if Alice's disks was 26 and Bob's was 39, and we picked P was 13, then in both of these cases, Alice would send 0, Bob would say 0, and conclude that the disk is the same. Okay? What saves us here is that we pick a rather large, but not too large prime. Okay? And let's analyze how this protocol actually works. It's a very interesting protocol, but not only for network protocols. Later we're going to use this to do very, very fast string matching. Probably a task that all of you do when you're searching on some web page and looking for some substring. Okay, so let's try to analyze what happens. The first thing that we want to figure out is how many primes are there. I'm hoping you all know the answer to this. Infinite, yes. This was discovered by Euclid 2,000 years ago. I know that you all know the proof. A better question is, how many primes are there that are less than, let's say, 2 to the 128? Oh, let's make this 2 to the 64. How many primes can fit into a 64-bit integer? How can you ask that? How can you answer that question? You can certainly count them, but that will take you a very long time here. Very good mathematician Gauss was 15 when he came up with an answer to this question. And it's known as this prime number theorem. And so what people say is they use this notation right here to basically stand for the number of primes. Yeah, here we go. So pi of x, in a number theory course, this will stand for the number of primes that are less than x. Okay? And it's a very cool theorem that pi of x is basically greater than x over log x. In fact, this squiggly line right here is the gaps are not meant to be there. They're rendering errors. This right here is actually pi x. You can sort of see that numbers, there's little plateaus like that, right? Little sections where things are straight. That's, for example, even numbers are never going to be prime, so there'll always be a little shelf. And in some case, like, 50, 51, 52, right? Those are three numbers which are not prime. So you can get some stretches, like 49, 50, 51, 52. None of those are prime. You get these little shelves. This right here is x over log x. And so you can sort of see that in this argument that this, by visual proof for the first few thousand, this is certainly true. Okay? This is what I want you to remember. The point is, there are lots of primes that are less than x. Okay? In particular, if we consider 64-bit numbers, this is basically saying that, so if x is around 2 to the 64, then pi of 2 to the 64 is greater than 2 to the 64 over 64, right? Which is 2 to the 58. So not only does Euclid say that there are infinite number of primes, it turns out that they're quite dense as well. So if you take a 64-bit number and pick it, just by chance, there's a 1 in 64 chance that it's going to be a prime number. So this also tells you that it's rather easy to pick a random prime. In fact, it's a little bit more complicated. You have to be able to test whether a number is prime. We'll talk about that on Thursday. But roughly saying, if you just pick a random 64-bit number, with some reasonable chance, with 1 over 64 chance, it's going to be a prime. So if you pick 64 numbers, with very high probability, one of those will be a prime. Okay? So this fact, the fingerprinting theorem, follows from these two things. This fact right here and the next very cool idea. Okay? So I want to argue that the number of prime divisors of x is less than log x. So I give you a number, let's say 10 million. How many prime divisors does 10 million have? And I'm going to claim that it's less than log base 2 of x. Here's the very cool argument. 2 is the smallest prime. If x has t prime divisors, then it has to be, each of those prime divisors has to be at least 2, right? Because 2 is the smallest prime. So if x has t prime divisors, then it has to be at least 2 to the t. That's the end of the proof. Does that make sense? 3, 5, 7, 11, 13, all of those are bigger than 2. So if I'm a number, and I have that one of those as a prime divisor, then certainly one of those 2's is going to be replaced by a larger number. It's kind of remarkable, huh? But all of you are capable of even writing this proof, right? So now, this fingerprinting idea is just a combination of these two ideas. That there are lots of primes, and that if you're a number, you can't have too many prime divisors. Okay? So, suppose that A, Alice's database, is not equal to B, but the protocol concludes with match. So the protocol made a mistake. Okay? So in this case, what has to happen is that A mod P has to equal B mod P, right? Because that's the only way that the protocol says match. And if we rearrange this, this means that A minus B is equal to 0 mod P. Everybody agree with that? If we just subtract B from both sides? What does it mean to be 0 mod P? Yeah, so P, right? P divides A minus B. Another, just the same way that you said, A minus B is a multiple of P. Now comes the question. How many prime divisors can A minus B have? Log, right? We just showed that, log of A minus B. Okay? So, let's combine these particular facts. So, this right here, A, remember, was of size 10 to the 8. Let's just call that 2 to the 40. Right, so a gigabyte is 2 to the 32. So this is like 256 gigabytes. We can change this. We can make it slightly bigger if you want. Doesn't matter. So this is certainly the size of your Dropbox. So that means log of A is roughly 40. Right? So take your hard drive, treat it like a number. It can have at most 40 prime factors. Very cool because there are lots of primes that are 64-bit numbers. So then the probability of failure, if we change our numbers around, let's call this way larger than your hard disk. Everybody follow that? No. Okay, so let's go over it again. Your hard disk, let's say, is 2 to the 64 bytes. Bits, let's say bits. Okay? So if you treat it as a number, when you subtract A minus B, that number is going to be at most a 2 to the 64-bit number. It's going to be of size 2 to the 64. Now if you take a log of that, it's 64. So that means if you treat your hard drive as a very big prime number, it's going to have at most 64 prime factors. Sorry, guys. Sorry. I'm losing a factor of 2 here. My original analysis is right there. So your hard disk has 2 to the 40 bits in it. So it's going to be a number of size. Okay, if you have 2 to the 40 bits, right, if you have 256 billion bits, the number that you're going to have is of size roughly 2 to the 2 to the 40. So taking the log is going to be 2 to the 40, which still gives you a reasonable chance here. Question? Remember here, we tried to figure out the number of primes that are less than, we want to know the number of primes that fit into a 64-bit integer. So we said, what is pi of 2 to the 64? By Gauss's theorem, which we haven't proven, we know that it's at least 2 to the 64 over 64, and this right here is roughly 2 to the 6. So if you put that together, it's around 2 to the 58. That's how many prime numbers there are that fit into a very big word. All right? So then, if you look at your disk as a number, it's going to be at most this big. If you take the log of it, it's going to be this big. The number of primes that are less than 64 bits are that many, and so you still have a very good failure rate. Obviously, if you take this to be like if you change this and allow yourself to choose 128 bits, okay, this is going to be, okay, 2 to the 121, so you can make this probability much, much better just by using, instead of 64 bits, using 128 bits. Still very small. The point is that if remotely, if you're in space, or I'm here, or Australia, wherever you are, you can check whether very large data sets are equal just by taking this hash. This is basically a hash. It's not a cryptographic hash, it's just a simple arithmetic hash. Okay, so why do I care about this? So we've gone through this analysis. I'm going to use this fingerprint. This technique is called Rabin fingerprinting. Michael Rabin came up with this idea in the early 1980s. And its main use, a very good use of it, is in the string matching problem. So consider you have the following problem. So you have some large corpus, you found some story on the internet, you're looking for a particular word. So for example, you're looking for Netflix, okay? And you want to find it in this particular database, in this particular corpus. You can imagine a number of simple algorithms. So the simplest one is that you take your corpus and your pattern and you compare this thing. And if they're not equal, then you shift over by one and compare the next block, right? And if they're not equal, then you shift over and compare the next block. Right? That is the brute force solution to this problem. What's the problem? And if obviously it has a 4-line implementation as well. What is the problem here? So if your pattern, if this corpus was of size n, and your pattern was of size m, just like this loop here shows, what would be the running time of this algorithm? In the worst case, exactly. It's terrible. Because if your input is, let's say, a gigabyte file, and your pattern is like 15 characters, it's going to take 15 billion comparisons, right? It's a very bad algorithm. And the problem is, for example, once you know that these characters mismatch, right, you're going to go through all of these repeated comparisons, all of these comparisons for the next thing, you're going to repeat, even though you don't have to. Now, there was a trick in the early 70s, I think, called the Knuth-Moyer-Pratt algorithm, and it solved this issue because the basic idea, we're not going to go through this algorithm, but I'm going to give you the basic idea. Once you know that these two characters mismatch, instead of repeating all this work, you're going to exploit the fact that you know that all of these characters were equal. So if all of these characters were equal, what is the next offset that I should attempt in order to make a match? Clearly, I shouldn't shift by 1 because I already know that A is not equal to B here, and the input had to be AB because I got all the way to this point for my first mismatch. Logically, where's the next thing you should check? What do you mean? You know that A is not going to be matched at offset 0, okay? What is the next possible offset that you should attempt to check? 4, exactly. Because you know that your pattern starts with AB, and the first mismatch happened right here, so the last two characters had to be AB. So the best next match to consider is essentially to shift this to this right here. Phrased in another way, the actual comparison you should make is that, so if you're given that the first Q characters of your pattern matches this section of the text, okay, but a mismatch occurs right here, then you should look for the longest prefix of your pattern
that is a suffix of your pattern and shift by exactly that much. So in this case right here, the longest prefix of my pattern that is a suffix of my pattern right here is 2. And so you should basically shift to wherever the first mismatch occurs, you should shift by 2 spots right there. That is called the Knuth-Moyer-Pratt algorithm, but it requires you to figure out what this complicated function is, right? What is the longest prefix that is also a suffix of my pattern? You could solve this. If you're really clever, you can do this Knuth-Moyer-Pratt algorithm in this much time, which is really good. It means you're doing a linear scan of your text and a linear scan of your pattern. Super efficient. But this requires a little bit of cleverness. What we're going to do instead, okay, what we're going to do instead is to use our idea from fingerprinting. Okay? So the idea is going to be like this. So we are going to treat, here's your pattern right here, and here is the actual corpus right here. We're going to say this was Alice's database right here, and Bob's database consists of a bunch of these particular. Each sliding window is like one of Bob's databases. Okay? So the algorithm is going to be as follows. We're going to pick a random t-bit prime number. We're going to compute the pattern mod this prime number, just like this is like Alice's operation. Okay? And then over the corpus, we're basically going to do Bob's operations. M is the size of the pattern. So we're going to do Bob's operations over sliding windows of that size. Okay? Everybody see what the algorithm is? So what is the probability of a mismatch at the first position? The first window. We just computed this for Alice and Bob fingerprint. If we use t-bit prime numbers, so in particular, let's use. So if the pattern is m bits long, then the pattern interpreted as a number has at most m prime divisors. And so the probability, what is the probability of mismatch at position 1? So I looked at the sliding window, I looked at this text, and I picked a random prime number, and it didn't match the first position 0. What's the probability it matches the second position? It's simple. You can at least upper bound it by the same number. There are n positions to match. So the probability that this algorithm fails is going to be upper bounded by, which is small. So what did I just argue here? I argued that the algorithm is going to work. All we're doing is running Alice and Bob, the fingerprinting example. We're just running it in several spots. Does everybody follow the algorithm? Okay. Let me give you an example. Let's work through this example. Suppose our pattern was this number, and suppose our text was this number. Let's pick a prime. What would you like? Can we use 13? 73 is a prime, so we could use that too. Let's go through what this algorithm would be. So someone compute 26535 mod 13. 2? Great. Okay, so here's what the algorithm is going to do. We're first going to compute this value, mod 13. What's that value? So our algorithm would say, clearly this is not a match. Now let's move to the next pattern, okay, which is 14159. And now we're going to try to compute 14159 mod 13, which is also not going to be 2. It's going to be, let's say it's 8. Okay? And eventually we'll get to this 26535, compute that mod 13, and we'll see that it's a 2. And at that point, we'll say we found a match. So do you understand the algorithm now? Okay, so question. Exactly. So that's what I was trying to analyze on this page right here. So clearly, when you pick 13 as a prime, it's not a good choice. Because you already have a 1 in 13 chance that you're going to hit, right? Just because 13, there are only 1 through 12. There are only a few numbers there. But what I'm going to say is that this algorithm is just like the fingerprinting algorithm that we talked about. We're just going to treat each of these sliding windows as a different version of Bob has. Instead of one database, now Bob has n databases. So what was the probability that that fingerprinting solution failed when Alice had 1 and Bob had 1? Well, that probability was very small, like roughly 2 to the negative 50, let's say. Now imagine we do it again. Still the failure rate is 2 to the negative 50. We do it again. Still the failure rate is 2 to the negative 50. So we can do it lots of times and still have a reasonable probability of success. The point is, precisely, if we use 128-bit prime numbers, then the probability that this algorithm makes a mistake is roughly upper bounded by this, which is still a small number. So that is to argue that the algorithm is correct. There's one more trick to try to argue how the algorithm actually works. So it would be terrible if, think about what we just did here. If given, once we've computed this number right here, 31415 mod 13, our next task is going to be computing 14159. Now if we do that division from scratch all over again, we haven't really saved anything. We've changed comparisons, which are, character comparisons with divisions, which, if you think about the simple gradebook division algorithm, it's going to take exactly the same time. Okay? So the question I have that I want you to ask right here is, given that you have 31415 mod 13, how can you compute the next slide, 14159 mod 13? Okay? Spend 3 minutes with your neighbor trying to figure that problem out. And a hint is that this number right here might be useful. Okay, so spend a few minutes. This is the core of this algorithm. Michael Rabin was a Turing Award winner. Lots of brilliant ideas, but you'll see how cool and simple this idea is for very fast string matching. Okay, spend a few minutes doing it. And I will actually find you some inspiring music. All right, so if you got into the electric slide idea here, consider this is the number that you started. You've already computed that once. Now, in order to get to its next sliding window, notice that what you're going to do is get rid of this 3 and add this 9. So in other words, you can write the next window is essentially minus 3 times 10,000, which 10,000 is just some constant, which is the size of the pattern. And you're adding the next number, right? So, question? Ah, yes. Okay, so this equation is true over the integers, so it's also going to be true mod p. And so what that means is if you have this mod p, and this mod p, and this mod p, then you can basically do one subtraction, one little multiplication right there, and one addition to get this value right here. So in this particular case, we have 7 minus 3 times 3, because 10,000 is 3 mod 13, and plus 9. So that should basically also be 7. What? 9 mod 13 is 9 still. Question. What do you have to multiply by 10? Ah, yes. Yes, you have to do a shift. You're right. You're absolutely right. Okay, so let's get this. So 7 minus 9 would be negative 2, times 10 would be negative 20, which would basically be 7, right? Okay. So, yeah, essentially we're going to do single-digit multiplications right here and a bunch of very simple mod operations. So in other words, this is going to be O of 1 single mod P operations. Okay, so if P is again a 128-bit word, then it's almost like a single machine instruction. It's a constant number of single machine instructions which lets you do the electric slide by one. Okay, so so that means that this algorithm right here is basically going to take this many mod P operations. So it's much simpler in practice than KMP to actually program, and works remarkably well. Now there are lots of genetic algorithms. So if you're looking for an undergraduate research project and you're also interested in genomics or biology, there are many interesting algorithms that bioinformatics people use to do string matching operations, and some of them are randomized and some of them use this type of hashing in order to check certain occurrences of patterns, etc. Okay. Very last example. I won't have time to finish it, but I want to introduce the question. Well, technically, this right here, this is like each bit of that, computing that requires, let's say, that many mod P operations as well. Any more questions about the string matching? It's the basis for many cool types of checks. If you want to check for palindromes or all sorts of shifts of patterns. No questions. Okay, last example. I won't be able to finish the analysis, but I want to get the problem started. So this is a communication problem. Suppose you have a large number of very small little wireless sensors, like wireless sensor network type of operation. So you have a bunch of these small sensors, and you want to scatter them across a field or throw them all across a desert, and you take some measurements of that desert. Okay? Eventually, you need each of these little motes, whatever, to communicate their information back to some central server, which can ship the data back to your analysis headquarters. So the question is, how can each of these little small devices communicate to some centralized server? And the constraints of this problem, obviously, if we could initialize each of these devices with some unique identifier and give them a specific time slot and so forth, we could perhaps organize some sort of network beforehand, before we send all these sensors into the wild. But imagine we don't have that luxury. Each of these receivers doesn't get to be initialized with some special number, or all you get to do is write some algorithm that says communicate your information back to the central server. Moreover, if two of these receivers tries to broadcast at the same time, then their signals, they're such weak signals that their signals will collide and interfere, and neither of their messages will get through. Okay? So how might each of these little transceivers use an algorithm in order to make sure that their message gets sent to the server? So at some point, you have 100 people, 100 little nodes. They want to broadcast their message to, let's say, a wireless router or some sort of sensor hub. And they haven't been able to prearrange like exactly what their topology is, who's connected to who or whatnot. And they want to send their message. What can you do? You can all try to speak as soon as you can. What would happen then? Everybody collides, yeah. Imagine all of you have the same burning question that you have for me about the string matching algorithm. Same time. Very good. Very good. So what do you have in mind? Good idea. But what if you and you both have the offset 17? It means that whenever you talk, both of you will always collide and never get your message sent to me. Good idea.
I think what you're saying though is like, assuming they get a
Yep. No. Let's not do that. Let's assume that we're all doing some computation. We'll all get the answer roughly at the same time. Now we want to send our information to the server. You're on the right track. So, any other suggestions? Your number could change. So what you're basically saying is that the first time you take some random number like 17, and you try to broadcast it times 17, then what? Maybe you switch your number. After that, you maybe take 54, and then broadcast it times 54. Yeah, that's roughly. This is in space.
Solar radiation.
Yeah, so I think the problem you're trying to address is randomness. We can assume that each of these nodes have a randomness. Let me give you an idea here, which is very much close to what you were suggesting. Here is the very simple protocol which actually works. So all you got to do at every time step, once you get your data, all you got to do is flip a coin with probability 1 over n, where n is the upper bound of the number of nodes. Let's call it 10,000, let's say. So when you're ready to speak, and whoever's ready to speak, what you do, which is probably what you do in class, because this is probably why it's so quiet and you don't ask questions, is you're probably flipping a coin, deciding whether you're going to speak or not, right? So you flip a coin. If you're heads, then you broadcast. If you're not heads, you wait. And you try this for n log n times. And with very high probability, you will get your message through. So the analysis of this is very interesting. Think about how simple these algorithms are. So that's one of the really key insights with randomness. There could be deterministic ways for doing some of these things. But in many cases, a randomized algorithm can be efficient and very simple. We've seen 3 examples of that today. So I'll see you on Thursday.